You are being pulled toward the center of the earth right now. Every second of every day, every moment you have ever lived, from the instant you were born to the moment you will die. A force invisible, silent, relentless has been dragging you downward your entire life. You have never escaped it, not once, not for a single second. Even when you jump, you are not escaping it. You are briefly losing the argument. Gravity always wins, always pulls you back, always reclaims you. It held you in your crib. It will hold you in your grave. It is the most constant companion you have ever had, more faithful than any person, more reliable than your own heartbeat. It has never taken a break, never wavered, never let go, and you have no idea what it is. No one does. This is not an exaggeration. This is not a rhetorical device designed to make gravity sound more mysterious than it is. This is the literal state of physics in the 21st century. We do not know what gravity is. We do not know what it is made of. We do not know why it exists. We do not know how it works at the most fundamental level. We can describe it. We can calculate it. We can predict its effects to extraordinary precision. We can launch spacecraft that travel billions of kilometers and arrive at their destinations within seconds of predicted schedules, navigating entirely by gravitational calculations. We can detect gravitational waves, ripples in space-time itself, produced by black holes colliding 1 billion light-years away. But we cannot explain it, cannot say what the thing is that we are so good at calculating, cannot identify the mechanism that produces the effect we measure so precisely. We have the what, we have the how, we do not have the why. Gravity is the oldest force known to science, the first to be described mathematically, the most familiar, the most obvious, the one you feel every moment of your life. And it is, by an enormous margin, the least understood. This is the story of how we discovered that the most familiar thing in the universe is also the strangest, and how the search for what gravity is made of led physics to the most disturbing question it has ever encountered. The myth says an apple fell on Isaac Newton's head. This almost certainly did not happen. What did happen was stranger and more important. Newton was 23 years old in 1666. Cambridge University had closed because of the plague, the bubonic plague, the Black Death. Students were sent home. Newton went to his mother's farm in Woolsthorpe, Lincolnshire. A small village. Fields, quiet, nothing to do but think. He thought for 18 months, and in those 18 months, alone in a farmhouse, while plague ravaged England, he invented calculus, developed his theory of optics, and formulated the law of universal gravitation. 3 of the greatest intellectual achievements in human history, produced by one person, in one place, during one plague. This is perhaps the most productive period of isolation in human history. A 23-year-old locked away from the world by disease, discovering the mathematical structure of the universe. No laboratory, no colleagues, no university, just a mind and the falling of objects and the question that no one else was asking. The apple story, if it has any truth, involves Newton watching an apple fall and asking a question no one had asked before. Not why does the apple fall? Everyone knew things fell. Aristotle had explained it 2,000 years earlier. Things fall because they seek their natural place. The natural place of heavy objects is the center of the earth. This was not a mathematical theory. It was a story, a narrative that explained the phenomenon without predicting anything, without providing a mechanism, without answering how. Newton asked how. And more importantly, how far does the falling extend? Does the force that pulls the apple down also pull the moon? Is the moon falling toward Earth the same way the apple is? Is the force that makes things drop to the ground the same force that keeps planets in orbit around the sun? Newton proved it was. The same inverse square law that describes an apple falling from a tree describes the moon orbiting the Earth and the Earth orbiting the Sun and Jupiter orbiting the Sun and every gravitational interaction in the universe. One law, one equation, universal, F equals G times M1 times M2 divided by R squared. The force between two objects is proportional to the product of their masses and inversely proportional to the square of the distance between them. G is the gravitational constant, a number, measured, not derived, not calculated from deeper principles, just measured. We know its value. We do not know why it has that value. We do not know why it exists. Newton's law worked spectacularly. It predicted the orbits of planets, explained the tides, described the trajectories of comets. For over 200 years, it was the most successful scientific theory ever created. It made the universe seem like a clockwork machine, predictable, deterministic, comprehensible. Wind it up and let it run. Every motion determined by the gravitational forces between masses. But Newton knew something was wrong, something deeply wrong, and he was honest enough to say so. That gravity should be innate, inherent, and essential to matter, so that one body can act upon another at a distance through a vacuum without the mediation of anything else, is to me so great an absurdity that I believe no man who has in philosophical matters a competent faculty of thinking can ever fall into it. Newton was describing his own theory and calling it absurd. The problem was action at a distance. How does the sun pull the Earth? How does the gravitational force travel 150 million kilometers of empty space instantaneously? What is the mechanism? What carries the force? What mediates the interaction? Newton had no answer. His law described what gravity does. It said nothing about what gravity is. The sun pulls the Earth. But how? Through what? By what mechanism? The question was unanswerable within Newton's framework. He knew it. It bothered him until the day he died. I have not been able to discover the cause of these properties of gravity from phenomena, he wrote, and I frame no hypotheses. He framed no hypotheses. He calculated, he predicted, he described, but he could not explain. 200 years of physics built on a foundation its creator acknowledged was fundamentally mysterious, and then Einstein arrived. Albert Einstein was working in a patent office in Bern, Switzerland, in 1907. He was 28 years old. He had already published special relativity 2 years earlier, already shown that space and time are not absolute but relative, already derived E equals mc squared, already begun reshaping the universe. And one afternoon, sitting at his desk evaluating patent applications, he had what he later called the happiest thought of my life. He imagined a person falling from a roof, not dramatically, not tragically, physically. He imagined the experience of free fall. What would a person feel while falling? Before hitting the ground in the pure moment of falling, what forces would they experience? The answer is none. A person in free fall is weightless. They feel no gravity, no force pulling them down, no sensation of weight, nothing. They float. They experience exactly what an astronaut experiences in orbit, because an astronaut in orbit is also falling, continuously falling toward Earth. The space station falls around the Earth in a curve that matches Earth's curvature. The astronaut inside feels no gravity. Not because gravity is absent, it is nearly as strong in orbit as on the surface, but because they are falling with it, moving along with the gravitational field rather than resisting it. Einstein realized this meant something profound. If a person in free fall feels no gravity, then gravity is not a force in the usual sense. A force is something you feel, something that pushes or pulls, something that accelerates you relative to your surroundings. But gravity does not do this. You feel weight only because the floor pushes up against you. Remove the floor, jump off a building, fall in an elevator, orbit the Earth, and the sensation of gravity vanishes completely, not because gravity stopped, because you stopped resisting it. Think about this. The force you have felt every moment of your life, the thing pulling you down, the weight in your bones, the heaviness you carry that is not gravity. That is the floor. That is the ground. That is the surface of the Earth, pushing against the soles of your feet, preventing you from following the path that space-time wants you to follow. What you call standing still is actually resisting the curvature of space-time. What you call falling is actually relaxing into it. The ground is the force. Gravity is the freedom. This is not how anyone thinks about gravity. This is not how it feels. It feels like gravity pulls you down and the ground saves you. Einstein showed it is the opposite. The ground pushes you up. And gravity, if it is anything, is the natural state of motion through curved space-time that the ground prevents you from following. Everything falls at the same rate. A feather and a bowling ball in vacuum. A person and a planet. Everything. The same acceleration, regardless of mass. No other force works this way. Electromagnetism depends on charge. The strong force depends on color charge. The weak force depends on weak isospin. Each force affects different particles differently based on their properties, but gravity affects everything equally. Everything falls the same way. Everything follows the same path. This is the deepest clue about gravity's nature. And for 300 years after Newton, no one understood what it meant. There is another clue. One that should disturb you. Gravity is absurdly weak. Incomprehensibly weak. The weakest force in nature by a margin so large it defies understanding. Pick up a paperclip with a small magnet. The magnet holds the paperclip against the gravitational pull of the entire Earth. One small magnet versus 6 trillion kilograms of planet. The magnet wins. Without effort, without strain. The electromagnetic force in a tiny magnet overpowers the gravitational force of an entire world. How weak is gravity compared to electromagnetism? Roughly 10, 36 times weaker. A 1 followed by 36 zeros. A trillion times weaker. If electromagnetism is the roar of a jet engine, gravity is quieter than the thermal vibrations of a single atom at absolute zero. If electromagnetism is the sun, gravity is a candle on the other side of the observable universe. Why? Why is gravity so weak? Why is the force that shapes the large-scale structure of the universe that forms galaxies, ignites stars, creates black holes so extraordinarily feeble compared to the forces that operate at atomic scales? This is called the hierarchy problem, and no one has solved it. No one has explained why gravity is 36 times weaker than electromagnetism. The number is not derived from any theory. It is not explained by any principle. It is simply a fact about the universe, a fact that cries out for explanation and receives none. Unless gravity is not what we think it is, unless gravity is not a fundamental force at all, unless gravity is something else entirely, something derived from a deeper level of reality, something emergent, something secondary, and its weakness is not a mystery, but a consequence of its emergent nature. Einstein saw that gravity is not a force at all, it is geometry. This is the equivalence principle, the most important insight in the history of gravity, and one of the most profound ideas any human being has ever had. Einstein spent the next 8 years working out the mathematics. 8 years, from 1907 to 1915. 8 years of the most intense intellectual effort in the history of science. 8 years of learning differential geometry, tensor calculus, Riemannian manifolds, mathematics that most physicists of his era had never encountered. He struggled, visibly, desperately. He made mistakes, published wrong equations, followed dead ends for months, wrote to friends that he was tormented by the problem, that he could not sleep. that the mathematics was beyond him, that he was working harder than he had ever worked in his life and making almost no progress. Marcel Grossmann, his mathematician friend from university, helped him with the geometry. Without Grossmann, Einstein might never have found the right mathematical framework. The collaboration was essential, but the physical insight, the vision of what gravity must be, was Einstein's alone. He knew what the theory had to say. He just could not find the language to say it. In November 1915, after 8 years of labor, he presented the field equations of general relativity to the Prussian Academy of Sciences. He gave 4 lectures over 4 weeks, each lecture refining the equations, each version closer to the truth. The final version, presented on the 25th of November 1915, was correct. He knew it immediately because it predicted the anomalous precession of Mercury's orbit, a tiny discrepancy that Newtonian gravity could not explain. Einstein's equations explained it exactly, perfectly, without any adjustable parameters. He later said that when he saw the Mercury result, his heart physically shuddered. He was beside himself with joy for days. He knew the theory was right. The equations are beautiful, not metaphorically, mathematically. They compress an extraordinary amount of physics into a compact, elegant form. Every physicist who encounters them for the first time feels something: awe, wonder, the sense that nature's deepest structure has been glimpsed. And what they say is this: gravity is not a force pulling objects through space. Gravity is the curvature of space itself. Mass and energy bend the fabric of space-time. Objects moving through curved space-time follow the straightest possible paths, geodesics, through the curved geometry. What we perceive as gravitational attraction is actually objects following the natural contours of curved space and time. The Earth does not pull the apple. The Earth curves the space-time around it. The apple follows the curvature. It moves along the straightest possible path through curved geometry. That path leads to the ground. What Newton called gravitational force, Einstein revealed as geometric curvature. The sun does not pull the Earth. The sun curves space-time. The Earth moves through that curved space-time along a geodesic. That geodesic is an elliptical orbit. What Newton calculated as gravitational attraction between masses, Einstein described as geometry. No force, no action at a distance, no mysterious mechanism pulling objects through empty space, just geometry, curvature, the shape of space-time itself. Newton's question, what carries the force across empty space, was answered by dissolving it. There is no force. There is no empty space. There is only curved space-time and objects moving through it. The question was wrong. The answer is not something carries the force. The answer is, there is no force to carry. This is one of the most profound shifts in the history of human thought. Newton described gravity as a force acting across distance. Einstein showed there is no force and the distance itself is part of the phenomenon. The stage is the actor. The background is the foreground. The container is the content. This is not metaphor, not analogy, not a teaching tool. This is what gravity is according to our best theory. Space and time are not a fixed stage on which physics happens. Space and time are dynamic participants in physics. They curve and stretch and warp in response to the matter and energy they contain. And that curvature is what we experience as gravity. General relativity has been tested more thoroughly than almost any theory in the history of science, and it has passed every test. It predicted that light bends around massive objects, confirmed during the solar eclipse of 1919 by Arthur Eddington. Starlight passing near the sun was deflected by exactly the amount Einstein predicted. The announcement made Einstein a global celebrity overnight. It predicted that time runs slower in stronger gravitational fields, confirmed by flying atomic clocks on airplanes, by comparing clocks at different altitudes, by GPS satellites. Your GPS phone corrects for gravitational time dilation every second it operates. Without general relativity corrections, GPS would drift by 11 kilometers per day. Your phone knows where you are because Einstein was right about gravity. It predicted gravitational waves, ripples in space-time produced by accelerating masses. Einstein predicted them in 1916. He doubted they were real. Changed his mind. Changed it again. Published a paper arguing they do not exist. The referee rejected the paper correctly because the paper was wrong. Einstein was furious. But the referee was right. Gravitational waves are real. Confirmed in 2015 by LIGO, the Laser Interferometer Gravitational Wave Observatory. 2 detectors, one in Louisiana, one in Washington State, each one 4 kilometers long. Laser beams bouncing between mirrors, measuring the distance with precision beyond anything previously achieved. On the 14th of September 2015, at 5:51 a.m. Eastern Time, both detectors registered a signal, a chirp, rising in frequency over 0.2 of a second. 2 black holes, each roughly 30 times the mass of the Sun, spiraling into each other 3 billion light-years away. Their collision released more energy than all the stars in the observable universe combined, but as gravitational waves, not light. Those waves traveled for 1.3 billion years across the cosmos. They reached Earth. They stretched and compressed space-time as they passed. LIGO detected the distortion. The amount of stretching was less than 1/10,000th the diameter of a proton, a distance so small it makes an atom look like a galaxy, the most sensitive measurement ever made by human beings. And it matched Einstein's prediction from 1,916 100 years earlier exactly. It predicted black holes, regions where space-time curvature becomes so extreme that nothing can escape, confirmed by the Event Horizon Telescope in 2019, which produced the first direct image of a black hole. The shadow, the accretion disk, the geometry of light bending around extreme curvature, all exactly as general relativity predicted. Every prediction confirmed, every test passed. Over 100 years of experiments, observations, and measurements. General relativity is one of the most successful theories in the history of science, and it is wrong. Not wrong in the sense that its predictions fail, they do not. Not wrong in the sense that a better theory gives different answers for the phenomena it describes. No theory does. General relativity is wrong in a deeper sense. It is incomplete. It describes gravity as geometry. It describes space-time as a smooth, continuous fabric that curves in response to mass and energy. And at everyday scales, planets, stars, galaxies, black holes, this description is perfect. But at the smallest scales at the quantum level, at distances smaller than 10, -35 meters, at the Planck scale, smooth, continuous space-time cannot exist. Quantum mechanics forbids it. Quantum mechanics says everything is quantized. Energy comes in discrete packets. Light is made of individual photons. Electric charge comes in units of the electron charge. Angular momentum is quantized. Every physical quantity that has been examined at the quantum level turns out to be discrete, not continuous, made of individual units, not smooth flows. If gravity is geometry, if gravity is the curvature of space-time, then space-time itself should be quantized at the smallest scales. Space should be made of tiny, discrete units. Space-time should be granular, not smooth. There should be a minimum length, a minimum time, a minimum chunk of space below which the concept of distance ceases to have meaning. But when physicists try to apply quantum mechanics to gravity, when they try to quantize space-time the way they quantized electromagnetism and the nuclear forces, the mathematics explodes. Infinities appear everywhere. Predictions become meaningless. The standard techniques that work perfectly for every other force in nature produce nonsensical results when applied to gravity. This is the crisis at the heart of modern physics. The two greatest theories of the 20th century, general relativity and quantum mechanics, are incompatible. General relativity describes gravity as smooth, continuous geometry. Quantum mechanics demands that everything at the fundamental level be discrete, quantized, probabilistic. Both theories are confirmed by experiment. Both are spectacularly successful in their domains, and they cannot both be right. This is not a minor technical difficulty. This is not a gap that can be bridged by better mathematics or more powerful computers. This is a fundamental contradiction in our understanding of reality. At the center of every black hole, where space-time curvature becomes infinite, general relativity breaks down. It predicts a singularity, a point of infinite density and infinite curvature. But infinite quantities in physics are not predictions. They are confessions. They are the theory saying, I cannot describe this. I do not know what happens here. Something else takes over, and I have no idea what it is. At the Big Bang, the origin of the universe, the same thing happens. General relativity predicts a singularity, the entire universe compressed to a point of infinite density. But this is where gravity and quantum mechanics collide most violently. At the moment of creation, both theories must apply simultaneously. Gravity because the curvature is extreme. Quantum mechanics because the scales are subatomic. And when you try to combine them, the mathematics produces nonsense. Infinities multiplying infinities. Predictions that are literally meaningless. The universe began at a point where our understanding of gravity fails completely. The most extreme objects in the universe, black holes, contain interiors where our understanding of gravity fails completely. The deepest questions about existence: how did reality begin? What happens at the center of a black hole? What is space-time made of? Are exactly the questions where the incompatibility between gravity and quantum mechanics matters most. One of them, or both, must be incomplete, must be an approximation of some deeper theory that unifies gravity with the quantum world. A theory of quantum gravity, the holy grail of theoretical physics, the most sought-after theory in the history of science. And we do not have it. After nearly a century of searching, we do not have a theory of quantum gravity. We do not know what gravity is made of at the quantum level. We do not know if space-time is fundamental or emergent. We do not know if gravity is truly geometry, or if geometry is a large-scale approximation of something deeper. Newton knew he did not understand gravity. He said so. Einstein replaced Newton's force with geometry. But Einstein knew his theory was incomplete. He spent his last decades trying to unify gravity with electromagnetism. He failed. And we, a century after general relativity, a century after quantum mechanics, still do not know what gravity is, the most familiar force, the most ancient companion. The thing that holds you to the ground and holds the moon in orbit and holds galaxies together and shapes the large-scale structure of the entire universe. We do not know what it is made of. And the search for the answer is leading physics to the most unexpected place imaginable. Every force in nature has a particle. Electromagnetism has the photon, the particle of light, the carrier of electric and magnetic forces. When two electrons repel each other, they exchange photons. When a magnet sticks to your refrigerator, photons mediate the attraction. When light enters your eyes and strikes your retina and creates the experience of vision, photons are doing the work. The electromagnetic force is carried by a particle. We have detected it, measured it, counted it, built technology around it. The strong nuclear force has the gluon. 8 varieties, carrying color charge, binding quarks into protons and neutrons. Binding protons and neutrons into atomic nuclei. Without gluons, no atoms would hold together, no chemistry, no matter, as you know it. The strong force is carried by a particle. We have detected it. At particle accelerators, in high-energy collisions, the gluon is real. The weak nuclear force has the W and Z bosons. 3 particles, massive, short-lived, responsible for radioactive decay, for the nuclear reactions that power the sun, for the process that converts hydrogen to helium inside stellar cores and releases the energy that lights the universe. Without the W and Z bosons, stars would not shine. The weak force is carried by particles. We have detected them at CERN. In 1983, Carlo Rubbia and Simon van der Meer received the Nobel Prize for the discovery. The pattern is clear, beautiful, consistent. Every force in nature is mediated by particles. Force is not a mysterious action at a distance. It is an exchange of particles. 2 electrons repel each other by throwing photons back and forth. 2 quarks attract each other by exchanging gluons. A neutron decays into a proton by emitting a W boson. Every force, at the quantum level, is a particle interaction. This pattern, called quantum field theory, is the most successful framework in the history of physics. Every prediction confirmed, every calculation matching experiment, every force explained through particle exchange. 3 forces, 3 sets of carrier particles, all detected, all measured, all integrated into the standard model of particle physics, the most successful and precise framework in the history of science. The standard model describes every known particle and every known force except one: gravity. Gravity should have a carrier particle. If the pattern holds, if gravity is a force like the other 3, then there should be a particle that mediates gravitational interactions, the way photons mediate electromagnetism. A particle exchange between masses, a quantum of the gravitational field, a fundamental unit of gravitational force. Physicists have a name for it: the graviton. They have calculated its properties. It should be massless like the photon. It should travel at the speed of light like the photon. It should have spin 2, unlike the photon, which has spin 1. This is important. The spin determines the nature of the force. Spin 1 particles produce forces that can attract or repel. Spin 2 particles produce forces that only attract. Gravity only attracts. The graviton must have spin 2. They have calculated how it should interact, how it should scatter, what its cross-section should be, how it should couple to matter and energy. The mathematics is consistent. The predictions are well defined. The particle makes theoretical sense. There is one problem. We cannot detect it, not now. Not with any technology we can currently imagine. Not with any technology that could plausibly be built in the foreseeable future. Perhaps not ever. The reason is gravity's extraordinary weakness. The same weakness that makes a small magnet overpower the entire Earth. The same factor of 10(36) that separates gravity from electromagnetism. That weakness means individual gravitons interact with matter so feebly that detecting a single graviton would require a detector larger than Jupiter, made of the densest material possible, operating at the lowest conceivable temperature, for a period longer than the age of the universe. This is not an engineering challenge. This is not a problem that better technology will solve. This is a fundamental limit. Freeman Dyson, one of the greatest physicists of the 20th century, argued in 2013 that detecting a single graviton is physically impossible. Not practically impossible, physically impossible. The energy required to make the detector sensitive enough would cause the detector to collapse into a black hole before it could measure anything. Think about this. The universe contains a particle if the graviton exists that is in principle undetectable. Not because we are not clever enough, not because our instruments are not sensitive enough, because the laws of physics themselves prevent its detection. The graviton, if it exists, is hidden behind a wall that no experiment can breach. This is unprecedented. Every other fundamental particle, every single one, was eventually found. Sometimes after decades of searching, sometimes requiring machines of extraordinary size and cost, but always eventually found: the photon, the electron. The neutrino predicted in 1930, so ghostly it can pass through a light year of solid lead without stopping, and yet detected in 1956. 26 years of searching, but found. The Higgs boson predicted in 1964, requiring the largest machine ever built by human beings, costing over $13 billion, employing thousands of scientists from dozens of countries. But found. In 2012, 48 years after prediction. The graviton is different. The graviton might be permanently beyond reach. Not 48 years, not a century, forever. The particle that carries the force you feel right now, if it exists, might be the one particle nature refuses to show you. And there is something almost theological about this, a force that shapes the universe, that holds galaxies together, that bends light around stars, that creates black holes. That governs the large-scale structure of everything. And at its most fundamental level, at the quantum level, where every other force reveals its particle nature, gravity hides, refuses to be seen, operates behind a veil that physics itself cannot lift. What kind of force hides this way? What kind of phenomenon refuses to reveal its fundamental nature? Every other particle in the Standard Model was predicted theoretically and then found experimentally. The photon predicted by Einstein in 1905, confirmed experimentally through the photoelectric effect. The W and Z bosons predicted by the electroweak theory in the 1960s, found at CERN in 1983. The Higgs boson predicted in 1964, found at the Large Hadron Collider in 2012 after a 50-year search costing billions of dollars. The graviton breaks this pattern. Theory predicts it. Experiment cannot find it. Not because we have not looked hard enough, because looking hard enough may be physically impossible. This should bother you. It should bother you deeply. Physics is an experimental science. A theory that cannot be tested is not physics. It is mathematics, or philosophy, or speculation. The graviton, the particle that should carry the force you feel every moment of your life, lives in a realm beyond experimental verification. It is the ghost in the machine. The particle that should exist but cannot be found. That must be there if gravity is a quantum force but hides behind the laws of physics themselves. Maybe the graviton exists and we simply cannot detect it. Many real things exist beyond our ability to observe them directly. We infer their existence from their effects. Dark matter has never been directly detected, but its gravitational effects on galaxies are unmistakable. Perhaps the graviton is similar real but forever indirect. Or maybe the graviton does not exist. Maybe gravity is not a quantum force. Maybe gravity is something else entirely. Something that does not fit the pattern of the other three forces. Something that operates by different rules. Something that is not carried by particles at all. Maybe gravity's refusal to be quantized is not a failure of our mathematics. Maybe it is a message from nature. Maybe nature is telling us that gravity is fundamentally different from the other forces. That treating it as just another force is the mistake. That the pattern photon gluon W and Z does not extend to gravity, because gravity is not in the same category. And the attempts to force gravity into that category have produced some of the most brilliant and most troubled theories in the history of physics. The first and most ambitious attempt is string theory. String theory proposes that every particle in the universe, every electron, every quark, every photon, every gluon, is not a point, but a tiny vibrating string. Different vibrations produce different particles. An electron is a string vibrating one way. A quark is a string vibrating another way. A photon is a string vibrating yet another way. All of matter and all of force emerge from the vibrations of one fundamental object. And one of those vibrations naturally, inevitably, without any additional assumptions, produces a massless spin, two-particle, a graviton. String theory does not add gravity to quantum mechanics. String theory produces gravity automatically. The graviton emerges from the mathematics whether you want it or not. This was the discovery that launched string theory from a failed theory of the strong force into the leading candidate for a theory of everything. John Schwartz and Michael Green demonstrated this in 1984. The story of that discovery is one of the great dramas of modern physics. Schwartz had been working on string theory for over a decade, largely alone, largely ignored. The physics community considered strings a dead end. Schwartz persisted. He believed the mathematics was too beautiful to be wrong, too elegant to be meaningless, too perfect to be an accident. In the summer of 1984, Schwartz and Green showed that a specific version of string theory, type IIB superstring theory, was mathematically consistent, free of anomalies, and contained gravity. The graviton emerged naturally from the vibrations of the string. Not forced, not added by hand. The way a guitar string naturally produces harmonics. The announcement electrified physics, the first superstring revolution, it was called. Within months, hundreds of physicists abandoned their previous research programs and began working on strings. Edward Witten, widely considered the greatest living theoretical physicist, called it the most important development in physics in decades. Witten's endorsement alone changed the field. When the most brilliant mind in theoretical physics says this is the direction, people follow. The elegance was intoxicating. One object, the string, one principal vibration, and from that, every particle, every force, every interaction, including gravity. The dream of unification, the dream that Einstein spent his last decades pursuing, seemed within reach. But string theory demands a price, a steep price. First, it requires extra dimensions, not 4 dimensions of space-time, 10 or 11, in the M-theory formulation that Witten proposed in 1995 to unify 5 different versions of string theory. 6 or 7 extra spatial dimensions beyond the 3 you experience. These dimensions must be compactified, curled up so small they are undetectable at current energies. The size of the extra dimensions determines the properties of the particles we observe. The shape of the compactification determines the laws of physics. And here is the problem. The number of possible compactifications is not small. It is not a few options that experiment could distinguish between. It is roughly 10, 500. A number so large it makes the number of atoms in the observable universe, roughly 10, 80, look like a rounding error. Each compactification produces a different universe with different particles, different forces, different constants of nature. String theory does not predict our universe. It predicts 10, 500 possible universes. Ours is one of them. But the theory does not say which one. This is the landscape problem. String theory produces a vast landscape of possible universes. Our universe is somewhere in that landscape, but string theory cannot tell us where, cannot predict the mass of the electron, cannot predict the strength of gravity, cannot predict any of the specific numbers that define our particular universe. The theory that was supposed to explain everything explains nothing specific. The theory that was supposed to be the final answer produces 10, 500 possible answers and cannot tell you which one is correct. Some string theorists embrace this. They propose the multiverse. All 10, 500 universes exist. We inhabit one, compatible with our existence. The Entropic principle, selection bias. We see the constants we see because only those constants produce observers to see them. Others are horrified. Lee Smolin, a leading loop quantum gravity researcher, wrote a book calling string theory not even wrong. Not wrong in the sense that it makes incorrect predictions. Not even wrong in the sense that it makes no predictions at all. A theory that predicts everything predicts nothing. A theory that is compatible with any possible observation is not a scientific theory. It is an unfalsifiable story. Peter Woit, a mathematical physicist at Columbia, titled his critique of string theory with the same phrase, "Not even wrong, the sharpest insult in science." A theory that cannot be tested is not physics. No matter how beautiful the mathematics, no matter how elegant the formalism, no matter how many brilliant people work on it. Second, string theory has made no experimentally testable predictions that differ from existing theories. After 40 years of work by thousands of the most talented physicists and mathematicians in the world, string theory has not produced a single prediction that could confirm or refute it. Not one. The strings, if they exist, vibrate at the Planck scale 10, -35 meters. To probe this scale directly would require a particle accelerator the size of the galaxy. This will never be built. String theory might be right. It might be the correct theory of quantum gravity. It might describe the fundamental structure of reality at the deepest level. But we may never know. The theory might be permanently beyond experimental reach. A beautiful, mathematically consistent, potentially correct description of the universe that can never be verified. Is this physics? Or is it mathematics that looks like physics? The debate has consumed theoretical physics for decades, and it remains unresolved. The second major attempt is loop quantum gravity, where string theory replaces particles with strings and adds extra dimensions. Loop quantum gravity takes a more conservative approach. It quantizes space-time directly. It takes Einstein's general relativity, where gravity is geometry, and applies quantum mechanics to the geometry itself. The result is radical. Space is not continuous, not smooth, not infinitely divisible. Space is made of discrete chunks, tiny loops of gravitational field woven together into a structure called a spin network, a fabric of quantized geometry. Each loop carries a quantum of area. Each node carries a quantum of volume. Space is granular at the Planck scale, like a fabric that appears smooth from a distance but reveals its weave when examined closely enough. The minimum area is roughly 10 -70 square meters. The minimum volume is roughly 10 -105 cubic meters. These are the Planck area and Planck volume. Below these scales, the concept of space ceases to have meaning. There is no smaller distance. There is no finer resolution. Space itself is pixelated. Imagine zooming in on the space in front of you. At normal scales, it looks empty, smooth, continuous. Zoom into the atomic scale 10, -10 meters, and you see atoms. Zoom to the nuclear scale 10, -15 meters, and you see protons and neutrons. Zoom further 10, -18 meters, and you see quarks. Keep zooming. Through 20 more orders of magnitude of empty smoothness, nothing but continuous space. Then, at 10, -35 meters, space itself changes. It stops being smooth. It starts showing structure. The loops appear. The weave of quantum geometry reveals itself. Space is not infinitely divisible. It has a grain, a texture, a finest resolution beyond which the question, what is between these 2 points, has no answer. Not because we cannot measure it, because there is nothing there to measure. Below the Planck scale, between does not exist. This is beautiful in its own way. It answers the question of what space is made of. Space is made of loops, quanta of geometry, discrete units of area and volume woven into the fabric of reality. Space-time is not a smooth background on which physics happens. Space-time is itself a quantum system, built from fundamental units the way matter is built from atoms. Loop quantum gravity resolves the singularities that plague general relativity. At the center of a black hole, where Einstein's equations predict infinite curvature, loop quantum gravity predicts a quantum bounce. The collapsing matter reaches maximum density, enormous but finite, and then bounces. The singularity is replaced by a bridge, possibly to another region of space-time. possibly to a new expanding universe. The Big Bang singularity is similarly resolved. Our universe may have bounced from a previous contracting phase. The beginning of time is not a singularity, but a transition. But loop quantum gravity has its own problems. It struggles to reproduce the smooth spacetime of general relativity at large scales. If space is discrete at the Planck scale, the continuous spacetime we observe should emerge as an approximation, showing that this emergence actually works, that the spin networks of loop quantum gravity reproduce Einstein's equations in the appropriate limit, has proven extraordinarily difficult. After 35 years of work, the emergence of smooth spacetime from discrete quantum geometry remains incomplete, and loop quantum gravity does not naturally include the other forces. String theory automatically produces gravity plus the standard model forces, at least in principle. Loop quantum gravity produces quantized spacetime, but says nothing about electromagnetism, the strong force, or the weak force. It is a theory of quantum gravity alone. Unification remains separate. There are other approaches. Causal dynamical triangulations build spacetime from simple geometric blocks and let quantum mechanics determine how they assemble. Causal set theory proposes that spacetime is a discrete set of events with a causal ordering but no continuous geometry. Asymptotic safety suggests that gravity might be quantizable after all, if the theory reaches a special fixed point at high energies where infinities tame themselves. Each approach captures some aspect of the problem. None has solved it. None has produced experimentally testable predictions. None has achieved the consensus of the physics community. After nearly a century of work, quantum gravity remains unsolved, and this should tell you something. 3 forces were quantized within decades of quantum mechanics being formulated. Electromagnetism quantized in the late 1940s by Feynman, Schwinger, and Tominaga. Quantum electrodynamics, the most precise theory ever created. Predictions confirmed to 12 decimal places. The weak force quantized in the 1960s by Glashow, Weinberg, and Salam. Unified with electromagnetism into the electroweak theory, confirmed at CERN, Nobel Prize. The strong force quantized in the 1970s. Quantum chromodynamics, asymptotic freedom, confirmed at particle accelerators worldwide, Nobel Prize. 3 forces, each quantized within 20 to 30 years of serious effort, each producing testable predictions, each confirmed by experiment, each integrated into a coherent framework. Gravity has resisted quantization for nearly 100 years. The most brilliant minds in the history of physics have worked on it. Einstein, Dirac, Feynman, Hawking, Penrose, Witten, Hooft, hundreds of others, thousands of papers, decades of effort, and we are no closer to a confirmed theory of quantum gravity than we were in the 1930s, when the problem was first identified. This is not normal. This is not how physics works. Physics solves problems. It took 20 years to go from Rutherford's discovery of the nucleus to quantum mechanics, 20 more to quantum electrodynamics, 20 more to the electroweak unification, 20 more to the standard model. Each generation of physicists built on the last. Each decade brought progress. Each problem yielded to sustained effort. Quantum gravity has yielded nothing. Not for lack of effort, not for lack of brilliance, not for lack of funding or attention or institutional support. The brightest minds, the deepest mathematics, the most sustained intellectual effort in the history of theoretical physics and gravity remains unquantized, unexplained at the fundamental level, mysterious in a way that no other force is mysterious. Why? Why does gravity resist? Why does the force that shapes the universe at the largest scales refuse to join the quantum framework that governs everything else? Why is the most familiar force the most mysterious? Maybe because gravity is not a force at all. Einstein told us this a century ago. Gravity is geometry. It is the curvature of space-time. And maybe the reason we cannot quantize gravity the way we quantize the other forces is that we are asking the wrong question. We are trying to find the particle that carries the force, but there is no force. There is only geometry. And geometry might not be made of particles. Geometry might be made of something else entirely. Something that is not a particle, not a string, not a loop, not a field. Something that the traditions have been pointing at for thousands of years. And that theoretical physics is only now beginning to glimpse. Maybe gravity's 100-year resistance is not a sign that we need better mathematics. Maybe it is a sign that we are looking in the wrong place. Like searching for the source of a river by walking downstream. Like trying to understand a shadow by studying the wall it falls on. Like trying to quantize a force that is not a force. Newton said gravity is a force. He knew this was wrong. Einstein said gravity is geometry. This was better, but incomplete. String theory says gravity is vibration. Beautiful but untestable. Loop quantum gravity says gravity is quantized geometry. Promising but incomplete. What if all of them are describing effects rather than causes? What if gravity, the thing that holds you to the ground, that holds the moon in orbit, that holds the universe together, is not a fundamental phenomenon at all? What if gravity is a consequence, an effect, a symptom of something deeper? What if gravity is made of information? The answer, if it is an answer, comes from the most unexpected direction. Not from particle physics, not from string theory, not from any attempt to quantize gravity from the top down, but from thermodynamics. From black hole physics, from the idea that gravity is not fundamental at all, that gravity is emergent, that gravity is what information does when it organizes itself. This is where we go in part 3, to the most radical proposal in the history of physics, the proposal that rewrites not just gravity but the nature of reality itself, and the evidence is more compelling than you expect. In January 2010, a Dutch physicist named Erik Verlinde posted a paper online that made the physics community lose its mind. The paper was 11 pages. The title was Calm, on the origin of gravity and the laws of Newton. The content was anything but calm. Verlinde proposed that gravity is not a fundamental force, not a curvature of space-time, not carried by a particle, not described by a field. Gravity, Verlinde argued, is an entropic force, an emergent phenomenon arising from the statistical behavior of microscopic information, the way temperature emerges from the random motion of molecules, the way pressure emerges from gas particles bouncing off container walls, the way the smooth flow of water emerges from the chaotic motion of trillions of individual water molecules. Temperature is not fundamental. No single molecule has a temperature. Temperature is a macroscopic description of microscopic chaos. Pressure is not fundamental. No single molecule exerts pressure. Pressure emerges when billions of molecules collectively push against a surface. These are emergent properties, real, measurable, consequential, but not fundamental. They arise from deeper microscopic dynamics. They do not exist at the level of individual particles. Verlinde said, gravity is the same thing. There is no gravitational force at the fundamental level. No graviton, no curvature, no field. At the fundamental level, there is information, bits of data encoded on surfaces, microscopic degrees of freedom organized in patterns. And when you zoom out, when you look at large numbers of these microscopic information units collectively, their statistical behavior produces what we perceive as gravity. The apple does not fall because a force pulls it. The apple falls because that is what happens when information on a holographic surface reorganizes in response to the presence of mass. The physics community reacted with a mixture of fascination and fury. Some called it the most important idea in decades. Others called it nonsense. The paper received hundreds of citations within months. Conferences were organized to discuss it. Rebuttals were published. Extensions were proposed. Arguments erupted in seminar rooms and on physics blogs and in the pages of journals. The fury was understandable. Verlinde was not a fringe physicist making extravagant claims. He was a professor at the University of Amsterdam, a string theorist, a serious researcher with a serious publication record. He had studied under Gerard Hooft, Nobel laureate, one of the architects of the Standard Model. His twin brother, Herman Verlinde, was also a distinguished physicist at Princeton. Eric Verlinde was an insider, a member of the establishment, and he was saying the establishment's most fundamental assumption that gravity is a force requiring quantization was wrong. Not approximately wrong. Categorically wrong. Wrong the way the Earth is the center of the universe was wrong. Not a small correction, but a complete reconceptualization. Gravity is not a force to be quantized. Gravity is a statistical effect to be derived. The search for the graviton is not just difficult, it is misguided. Like searching for the particle of temperature, like looking for the atom of pressure. You will never find it because it does not exist. Because if Verlinde is right, everything changes. To understand Verlinde's proposal, you need to understand a connection that was discovered decades earlier. A connection between gravity and thermodynamics that should not exist. That has no obvious reason to exist. And that keeps getting deeper the harder physicists look at it. It begins with Jacob Bekenstein and Stephen Hawking. We met them in the quantum series. Bekenstein showed that black holes have entropy disorder, information content proportional to the area of their event horizon. Hawking showed that black holes have temperature, they radiate thermal energy at a specific temperature inversely proportional to their mass. Together, Bekenstein and Hawking established that black holes are thermodynamic objects. They have entropy, they have temperature, they obey the laws of thermodynamics. This was shocking. Thermodynamics is the physics of heat engines and steam and gases and molecules bouncing around in containers. It was developed in the 19th century to make better steam engines. To understand why heat flows from hot to cold, to calculate the efficiency of machines. It is the most practical, most industrial, most earth-bound branch of physics. General relativity is the opposite. It is the physics of curved spacetime and cosmic geometry, of black holes and gravitational waves, and the expansion of the universe. It is the most abstract, most cosmic, most otherworldly branch of physics. These two branches of physics should have nothing to do with each other. Steam engines and black holes, heat flow and space-time curvature, entropy and event horizons. They belong to different centuries, different scales, different worlds. And yet, a black hole is a geometric object. It is a region of space-time with specific curvature properties. Its event horizon is a geometric surface defined by the equations of general relativity. Nothing about its description involves temperature or entropy or any thermodynamic concept. And yet black holes behave exactly like thermodynamic systems. They have temperature, they have entropy. They obey the four laws of thermodynamics with geometric quantities playing the roles of thermodynamic quantities. The area of the event horizon is entropy. The surface gravity is temperature. The mass is energy. The equations of black hole mechanics are mathematically identical to the laws of thermodynamics. Not similar, identical. The same equations with different symbols. Why? Why does geometry behave like thermodynamics? Why does space-time curvature have temperature? Why does a geometric surface have entropy? These questions haunted a generation of physicists. And in 1995, a theoretical physicist named Ted Jacobson answered them in a way that nobody expected, and nobody has been able to forget. Jacobson asked a simple question. If black hole horizons have thermodynamic properties, what about other horizons? A black hole horizon is special It is a surface beyond which nothing can escape. But it is not the only horizon in physics. An accelerating observer also has a horizon. If you accelerate constantly in a specific direction, there is a region of space-time that your signals can never reach, and from which signals can never reach you. You have a horizon, called a ridddle horizon, and this horizon also has thermodynamic properties. This is the Unruh effect, predicted by William Unruh in 1976. An accelerating observer perceives empty space as filled with thermal radiation. The vacuum is not empty for an accelerating observer. It glows. It has temperature. The temperature is proportional to the acceleration. Think about what this means. Two observers in the same location, one floating freely, one accelerating. The floating observer looks around and sees empty space. Vacuum, nothing. The accelerating observer looks around and sees a warm bath of particles, radiation, heat, temperature. They are in the same place. They are looking at the same vacuum, and they see different things. For one, the vacuum is cold and empty. For the other, it is warm and full. The vacuum, the emptiest possible thing, the absence of everything, has temperature, not intrinsically, not for everyone. But for an accelerating observer, nothingness itself becomes something. Emptiness glows. The void radiates. The temperature is tiny for ordinary accelerations. You would need to accelerate at roughly 10-20 meters per second squared, 100 billion times the acceleration of gravity on Earth, to raise the vacuum temperature by 1 degree Kelvin. This is far beyond any technology. The Unruh effect has not been directly measured, but it follows rigorously from quantum field theory. It is as well established theoretically as Hawking radiation, and it creates a bridge between concepts that should have nothing to do with each other. This means acceleration and temperature are related, not metaphorically, not by analogy, through precise mathematical equivalence. And since Einstein showed that acceleration and gravity are equivalent, the equivalence principle, this means gravity and temperature are related. Gravity equals acceleration. Acceleration equals temperature. Therefore, gravity equals temperature. This chain of reasoning is not speculative. Each link is established physics. The equivalence principle is confirmed by experiment. The Unruh effect follows from quantum field theory in curved spacetime. The connection between gravity and thermodynamics is built into the foundations of physics. Jacobson took this seriously, more seriously than anyone before him. He asked, what if this connection is not a coincidence? What if it is not a curious mathematical parallel? What if the thermodynamic properties of horizons are the fundamental level, and gravity, Einstein's beautiful geometric theory, is derived from them? He assumed that horizons have entropy proportional to their area, the Bekenstein-Hawking formula. He assumed that energy flowing across a horizon satisfies the first law of thermodynamics, conservation of energy, in its thermodynamic form. He assumed the Unruh temperature for accelerating observers. And from these assumptions, purely thermodynamic assumptions about horizons and entropy and temperature, he derived Einstein's field equations of general relativity. Read that again. He did not start with general relativity and derive thermodynamic properties. He started with thermodynamics and derived general relativity. He showed that Einstein's equations, the equations that took Einstein 8 years of agonizing intellectual labor to discover, the equations that describe how mass curves, space-time, the equations that predict black holes and gravitational waves, and the expansion of the universe, are a consequence of thermodynamics applied to horizons. Einstein spent 8 years searching for these equations, 8 years of learning new mathematics, 8 years of false starts and wrong turns. He later said it was the hardest intellectual work of his life. The equations seemed to come from the deepest level of reality, from the fundamental structure of space-time, from the bottom of physics. Jacobson showed they come from the top, from thermodynamics, from statistics, from counting bits of information on surfaces, and applying the laws of heat and entropy. The most profound equations in the history of gravity are not fundamental laws, they are emergent descriptions. They arise from something deeper. This is like discovering that the laws of fluid dynamics, the equations that describe how rivers flow and oceans move and weather patterns form, are not fundamental laws of nature, but consequences of molecular motion, which they are. We know this. The Navier-Stokes equations emerge from the statistical mechanics of molecules. No one thinks fluid dynamics is fundamental. Everyone knows it is emergent. Jacobson showed that gravity might be in the same category, not fundamental, emergent, arising from microscopic information dynamics, the way fluid flow arises from molecular chaos. This is one of the most important results in theoretical physics in the last 50 years, and it is largely unknown outside the physics community. Jacobson's 1995 paper has been cited over 2,000 times. It has been called the most important paper in quantum gravity that nobody talks about. The result has been extended, generalized, and confirmed by multiple independent derivations. No one has found a flaw in the logic. If Jacobson is right, then Einstein's equations are not the fundamental laws of gravity. They are emergent. They arise from deeper microscopic physics the way the laws of fluid mechanics arise from the molecular dynamics of water. You do not need to know about individual water molecules to describe how rivers flow. The equations of fluid dynamics are effective descriptions of collective behavior. Similarly, you might not need to know about individual atoms of spacetime to describe how gravity works. Einstein's equations might be the fluid dynamics of spacetime. Verlinde took Jacobson's insight and pushed it further, much further. Jacobson showed that Einstein's equations emerge from thermodynamics. Verlinde wanted to show that Newton's law of gravity F equals G, m1, m2 over r squared, also emerges from thermodynamics. Not as an approximation of general relativity, directly. From first principles, from information and entropy. His argument uses three ingredients. First, the holographic principle. The information content of a region of space is encoded on its boundary surface. The number of bits on the surface is proportional to the area measured in Planck units. Second, the equipartition theorem, a result from statistical mechanics. The average energy per degree of freedom in a thermal system is 1/2 times Boltzmann's constant times temperature. Energy distributes itself equally among available degrees of freedom. Third, the Unruh temperature. An accelerating observer perceives a temperature proportional to their acceleration. This connects motion through space-time to thermodynamic quantities. From these three ingredients, all established physics, all experimentally or theoretically grounded, Verlinde derives Newton's law of gravity, the inverse square law, the gravitational constant g. The whole thing, not approximately, exactly, from information, entropy, and temperature, the derivation is elegant. Consider a particle of mass m approaching a holographic screen, a surface encoding the information about the region beyond it. The particle's approach changes the information on the screen. Specifically, it shifts the entropy of the screen by an amount proportional to the particle's displacement. This entropy change, combined with the Unruh temperature and the equipartition theorem, produces a force. That force is exactly Newtonian gravity. Gravity emerges from the tendency of information to maximize entropy. The apple falls not because space-time is curved, not because a graviton carries a force. The apple falls because its motion toward the Earth increases the total entropy of the holographic surface between them. Gravity is an entropic force. The universe's drive toward disorder, toward maximum entropy, toward the most probable configuration of information manifests as the force that holds you to the ground. This is the second law of thermodynamics. Entropy always increases, disguised as gravity. The most fundamental law of thermodynamics, the one law that has never been violated in any experiment, the one law that physicists believe is absolutely inviolable. That law, applied to information on holographic surfaces, produces the phenomenon you have felt every moment of your life. Newton asked, "What is the mechanism that carries gravitational force across empty space?" The answer, if Verlinde is right, there is no mechanism, there is no force, there is entropy, there is probability. There is the statistical tendency of information to spread out, to disorder, to reach the most likely configuration. And when mass is present, that tendency looks like attraction, like falling, like gravity. The universe is not pulling you down. The universe is maximizing its entropy, and you are part of the calculation. Think about what this means for you. Right now, sitting wherever you are, the weight you feel, the heaviness in your body, the pressure of the chair against your back, the constant downward pull that has accompanied every moment of your life might not be a force at all. It might be information, bits of data on a surface you cannot see, reorganizing themselves in response to your presence, and the statistical tendency of that reorganization producing what you experience as gravity. You are being pulled toward the center of the Earth. But perhaps pulled is the wrong word. Perhaps you are being statistically nudged, entropically guided, informationally directed. The universe is not reaching out with an invisible hand and dragging you downward. The universe is simply doing what it always does, maximizing entropy, increasing disorder, following the probabilistic flow toward the most likely configuration, and gravity is what that process looks like when mass is involved. This is not how gravity feels. Gravity feels real, fundamental, immediate, like a force, like something pushing and pulling, like the most concrete, most tangible, most undeniable fact about physical existence. But temperature feels real too, and temperature is not fundamental. Pressure feels real, and pressure is not fundamental. The smoothness of water feels real. And at the molecular level, water is chaotic, discontinuous, nothing like the smooth fluid you experience. Emergence is the rule, not the exception. The macroscopic world is almost entirely made of emergent phenomena that feel fundamental but are not. Maybe gravity is the deepest emergence of all, the emergence that creates the stage spacetime itself on which all other emergence occurs. Verlinde's proposal connects directly to the ideas we explored in the quantum series. If gravity is emergent from information on holographic surfaces, then gravity is fundamentally connected to the holographic principle, and the holographic principle is fundamentally connected to quantum entanglement. And quantum entanglement is the phenomenon that makes the universe non-local, that connects particles across arbitrary distances, that suggests space itself might be emergent. The chain is remarkable. Entanglement creates spatial connectivity. Van Ramsdonk showed this. Spatial connectivity is described by geometry. Einstein showed this. Geometry obeys thermodynamic laws. Jacobson showed this. Thermodynamic laws applied to information produce gravity. Verlinde showed this. Entanglement, space geometry, thermodynamics, gravity. Gravity is not at the bottom of this chain. Gravity is at the top, the surface, the last thing to emerge, the macroscopic consequence of microscopic quantum information. The most familiar force in the universe, the one you feel every second of your life, might be the furthest thing from fundamental. This is a complete inversion of how we normally think about physics. We think of gravity as basic, primal, the force that comes first, the force that shapes the large-scale structure of the universe, the force that was there at the Big Bang, pulling matter together to form the first structures, the first stars, the first galaxies. But if gravity is emergent from entanglement and information, then gravity is not first. Information is first. Entanglement is first. Quantum correlations are first. The invisible web of connections that links every particle to every other particle that is the foundation. Gravity, the visible, tangible, obvious force that you feel right now, is the surface phenomenon. The derived quantity, the emergent effect, the thing you can feel is not fundamental. The thing you cannot feel, quantum entanglement, holographic information, microscopic bits on invisible surfaces, is fundamental. The obvious is emergent. The hidden is primary. And at the bottom of the chain, at the foundation, at the level that generates everything above it, is information. Quantum information, entanglement, correlations, bits. Wheeler said it from bit. Reality from information. Every particle, every force, every field, every geometric structure derives from information. And now, gravity, the force that shapes the cosmos, that creates black holes, that bends light, that holds galaxies together, might also derive from information, might be the most spectacular example of it from bit in the universe. But is Verlind right? Honesty requires this question, and the honest answer is, we do not know. Verlinde's proposal is compelling, mathematically consistent, and connects to established results like Jacobson's derivation and the holographic principle. It explains gravity's weakness. An emergent force should be weak compared to fundamental forces, because it arises from collective statistical behavior rather than direct microscopic interaction. It explains why gravity cannot be quantized like the other forces, because gravity is not a force in the same category. You cannot quantize temperature either. You cannot find the temperature particle. Temperature is collective, not fundamental. If gravity is collective, the search for the graviton is searching for something that does not exist. But there are problems. Verlinde's original derivation works for non-relativistic gravity, Newton's law. Extending it to full general relativity is more difficult. Jacobson's derivation shows that Einstein's equations follow from thermodynamics, but whether Verlinde's entropic force framework reproduces all of general relativity in all regimes remains under investigation. More importantly, the proposal has not been experimentally confirmed in ways that distinguish it from standard gravity. The predictions of entropic gravity and standard gravity are identical in most situations. Where they differ in the behavior of gravity at very large scales, in the dynamics of galaxies without dark matter, the evidence is mixed. Verlinde proposed in 2016 that entropic gravity might explain galaxy rotation curves without dark matter. Some observations support this, others do not. The jury is out. And some physicists reject the entire framework. They argue that gravity is fundamental, that the thermodynamic properties of horizons are consequences of gravity rather than the other way around, that Jacobson's derivation is a mathematical curiosity, not a deep truth, that Verlinde's entropic force is a clever reformulation, not a revolution. The debate continues. The evidence is incomplete. The question is open. But the direction is extraordinary. Whether Verlinde's specific proposal survives or not, the connection between gravity and information is established. Bekenstein's entropy, Hawking's temperature, Jacobson's derivation, the holographic principle, ADS divided by CFT, ER equals EPR. All of these point in the same direction. Gravity is connected to information. Space-time is connected to entanglement. The macroscopic geometry of the universe is connected to microscopic quantum data. Something is hiding underneath gravity. Something informational. Something quantum. Something that makes gravity not the foundation of reality but a consequence of it. A surface phenomenon. An emergent description. A shadow on the wall of Plato's cave. And the shadow is precise, extraordinarily precise. Gravity is tuned, not just in its strength, the hierarchy problem, the factor of 10, 36, but in its nature. Gravity curves space-time in exactly the way required to form stable orbits. Stable orbits are required for stable solar systems. Stable solar systems are required for stable planets. Stable planets are required for stable chemistry. Stable chemistry is required for life. Life is required for consciousness. If gravity were slightly stronger, stars would burn through their fuel in millions of years instead of billions. Not enough time for evolution. If gravity was slightly weaker, stars would never ignite. No fusion, no heavy elements, no carbon, no chemistry, no life. If gravity did not follow an inverse square law, if the force dropped off as the cube of distance instead of the square, there would be no stable orbits, no solar systems, no planets, nothing but chaotic trajectories and isolated objects tumbling through empty space. The specific properties of gravity, its strength, its range, its mathematical form, are precisely what is needed for a universe that produces conscious observers. Change any of them and the universe goes dark, goes dead, goes empty. And if gravity is emergent from information, if its properties are determined by the organization of microscopic data on holographic surfaces, then someone or something organized that data in exactly the right pattern. The information at the fundamental level is arranged so that the emergent gravity has exactly the properties needed for stars and planets and chemistry and life and consciousness. Is that arrangement accidental? Is it random? Is it the inevitable consequence of mathematical law? Or is it design? And if gravity is a shadow, if the force that shapes the cosmos is not fundamental but emergent, not a cause but a consequence, not the ground floor but the top floor, then what is the ground floor? What is the thing that gravity emerges from? What is the information whose entropy produces the force that holds you to the Earth? What is the fundamental level of reality that generates space-time and geometry and curvature and everything you experience as the physical world? And who or what organized that information in the specific pattern that produces a universe with gravity precisely tuned to allow stars and planets and chemistry and biology and consciousness? These questions wait in part 4, the final part, where we confront the deepest implication of entropic gravity. If gravity is made of information, and information requires organization, and organization implies structure, and structure implies design, or at the very least, raises the question of design, then the force that holds you to the ground might be the most profound evidence for something beyond physics that science has ever encountered. Or it might be the most spectacular example of emergence from blind mathematical law that nature has ever produced. The answer determines not just what gravity is made of, it determines what reality is made of, and whether reality was made. Let us be clear about where we are. We started with the most familiar force in the universe, the one you feel right now, the one that has held you to the ground every second of your life, the one so obvious, so constant, so unremarkable that you stopped noticing it decades ago, and we have discovered that nobody knows what it is. Newton described it as a force, an invisible pull between masses across empty space. He knew this was wrong. He said so. He called his own description so great an absurdity that no thinking person could accept it. But it worked. For 200 years it worked. So everyone used it, and nobody asked what the force actually was. Einstein replaced the force with geometry. Gravity is not a pull. Gravity is the curvature of space-time. Mass bends the fabric of the universe. Objects follow the curves. What you feel as weight is not a force dragging you down. It is the ground pushing you up, preventing you from following the natural curvature of space-time. Einstein's description is beautiful, confirmed by every experiment, accurate to extraordinary precision, and incomplete. Because at the quantum level, at the level where every other aspect of nature reveals its fundamental structure, gravity breaks, the equations produce infinities. The geometry becomes meaningless, the description fails. The search for a quantum theory of gravity has consumed a century. String theory proposes vibrating strings in 10 dimensions, mathematically elegant, experimentally untestable. 40 years of work by thousands of brilliant physicists, and not a single testable prediction. Loop quantum gravity proposes quantized geometry space itself, made of tiny discrete loops woven into a fabric of quantum structure. Conceptually radical, technically incomplete. 35 years and still no proof that smooth spacetime emerges from the quantum weave. Neither has produced a confirmed prediction. Neither has achieved consensus. Neither has answered the question, what is gravity made of? And then a different idea emerged, not from particle physics, not from string theory, from thermodynamics, from information theory, from the discovery that gravity has temperature, that horizons have entropy, that Einstein's equations can be derived from the laws of heat applied to microscopic information on surfaces, that Newton's law of gravity emerges from the statistical behavior of bits information maximizing entropy on holographic screens. Gravity might not be a force, might not be geometry, might not be a particle or a string or a loop. Gravity might be information, an emergent phenomenon arising from the organization of data at the most fundamental level of reality. And this raises the question that has been building since part 1. The question that every equation, every experiment, every failed attempt to quantize gravity has been circling. The question that physics alone cannot answer but can no longer avoid. If gravity is made of information, who organized the information? Before we reach for theology, let us exhaust physics. Let us be rigorous about what the informational view of gravity implies. Let us follow the logic without flinching. If gravity is emergent from microscopic information, then the properties of gravity are determined by the organization of that information. The strength of gravity, the inverse square law, the way gravity couples to mass and energy, the specific equations that govern gravitational dynamics, all of these emerge from and are determined by the pattern in which fundamental information is arranged. Change the pattern, change gravity. A different organization of the same fundamental bits would produce a different emergent force, different strength, different range, different mathematical form, different consequences for the macroscopic universe. The pattern that exists, the actual organization of information at the fundamental level of our universe, produces gravity with very specific properties. Properties that are fine-tuned for complexity, for structure, for life, for consciousness. The gravitational constant g has a specific value, 6.674 times 10, negative 11 cubic meters per kilogram per second squared. This number is not predicted by any theory, not derived from any deeper principle. It is simply measured, and it is precisely the value needed for a universe like ours to exist. If G were 10 times larger, stars would burn through their hydrogen fuel in a few million years. Not enough time for planetary systems to stabilize, not enough time for chemistry to produce complex molecules, not enough time for life. The universe would be a frantic, brief fireworks display of stellar explosions and then darkness. If G were 10 times smaller, stars would struggle to ignite. The gravitational compression at the center of a forming star would be insufficient to trigger nuclear fusion. No fusion means no starlight. No starlight means no energy for planetary surfaces. No energy means no chemistry. No chemistry means no life. The universe would be a cold, dark collection of gas clouds that never became anything. If gravity did not follow the inverse square law, if it dropped off as the cube of distance, for example, orbital mechanics would be fundamentally different. No stable, circular, or elliptical orbits. Planets would either spiral inward into their stars or fly off into interstellar space. No stable solar systems. No stable anything. Chaos at every scale. If gravity did not couple universally to all forms of mass and energy, if it interacted with some particles but not others, the way the other forces do, the universe would lack the coherent large-scale structure that produces galaxies, galaxy clusters, and the cosmic web. Without universal coupling, Gravity could not organize matter at the largest scales. The universe would be homogeneous soup forever. No structure, no complexity, no anything. There is more. Gravity operates in 3 spatial dimensions. In 3 dimensions, the inverse square law produces stable orbits. In 4 spatial dimensions, the force would drop off as the cube of distance and no stable orbits would exist. In 2 spatial dimensions, gravity would not drop off at all, and the universe would be a compressed, featureless plane. 3 dimensions is the only number of spatial dimensions in which gravity produces the rich orbital mechanics required for solar systems, planetary stability, and the complex gravitational dance that allows galaxies to form and persist. Why 3? Why not 4? Why not 7? Why not 26, the number of dimensions in bosonic string theory? There is no mathematical reason why the universe should have 3 large spatial dimensions. It is a choice, a selection, a specific number picked from an infinite set of possibilities, and it is the one number that makes gravity work for structure and complexity and life. The coincidences pile up, the strength of gravity relative to the other forces, the mathematical form of the gravitational law, the number of spatial dimensions, the universality of gravitational coupling, the specific value of the gravitational constant. Each individually might be dismissed as unremarkable. Together, they form a pattern so specific that the probability of its arising by chance, if such a probability can even be calculated, is vanishingly small. Each of these properties, the strength, the range, the universality, the mathematical form, the dimensionality, is determined by the pattern of fundamental information. Each is fine-tuned for a universe that produces complexity. And together they constitute an arrangement of information so precise, so specific, so improbable, that the question of whether it was organized by accident or by intention is not a theological question. It is a scientific question, a question about the probability of this specific pattern emerging from random initial conditions. The standard response from physics is the multiverse. Perhaps there are 10, 500 different universes, the string theory landscape, each with different fundamental information patterns, different emergent forces, different gravitational constants. In most of these universes, gravity is too strong or too weak, or the wrong mathematical form. Those universes are sterile, dead, empty of observers. We exist in the one that works, because we can only exist in the one that works. Selection bias. Anthropic principle. No design required. This is logically valid. It is a possible explanation. But notice what it requires. It requires 10, 500 unobservable universes to explain the properties of one observable universe. It replaces one extraordinary claim that the information was organized by a designer with another extraordinary claim that an incomprehensibly vast number of unobservable universes exist. Neither claim is testable, neither is falsifiable, neither is empirical. Both are metaphysical commitments disguised as scientific hypotheses. The irony is exquisite. The multiverse was invented to avoid the appearance of design, to provide a naturalistic explanation for fine-tuning, to keep God out of the equations. And in doing so, it created an entity, the multiverse, that shares many of God's properties. It is unobservable, it is unfalsifiable, it must be taken on faith. It explains everything. It predicts nothing specific. It is invoked to account for the otherwise inexplicable. Replace multiverse with God in most arguments for the multiverse, and the logical structure is identical. The physicist who dismisses God as an untestable hypothesis and then embraces the multiverse as an explanation has not escaped metaphysics. They have chosen a different metaphysics, one that trades a single intelligent organizer for an infinite collection of unintelligent random experiments. Both explain the data. Neither can be confirmed. The choice between them is not scientific. it is philosophical, and honest physicists admit this. Steven Weinberg, Nobel laureate, devout atheist, one of the most brilliant theoretical physicists of the 20th century, acknowledged that the anthropic principle makes him queasy, not because it is wrong, because it is the kind of explanation that does not feel like physics. It explains everything and predicts nothing. It is unfalsifiable by design. It is, in his words, the kind of argument that should be a last resort. And yet, for the fine-tuning of gravity, the anthropic argument might be the only non-theistic explanation available, because the tuning is extreme, not slight, not marginal, extreme. The gravitational constant is tuned within narrow margins. The inverse square law is the only mathematical form that produces stable orbits in 3 spatial dimensions. The universality of gravitational coupling is a unique property that no other force shares. Every aspect of gravity seems optimized for a universe that produces observers. Now listen to what the traditions say. Not about gravity specifically, about attraction, about the force that holds things together, about the principle that unifies the many into one. Because gravity, whatever it is the force of cosmic unity, the force that gathers matter into stars, stars into galaxies, galaxies into clusters, clusters into the cosmic web. Gravity is the organizing principle of the universe, the force that takes scattered dust and builds structure, that takes chaos and creates order, that takes separation and creates connection. In Hinduism, the force that holds the cosmos together is called Dharma, not in its ethical sense, in its cosmic sense. Rita, in the Vedas, the principle of cosmic order, the force that keeps the sun in its path, that keeps the seasons cycling, that keeps the universe from dissolving into chaos. The Rig Veda says, "By Rita the sun shines, by Rita the winds blow, by Rita the rivers flow," the sustaining force that maintains the structure of creation. Gravity by another name, the principle that prevents the universe from flying apart. In Islam, one of the 99 names of God is Al-Jami, the gatherer, the one who brings things together, who assembles the scattered, who organizes the dispersed. Another name is Al-Muqit, the sustainer, the one who maintains, who holds in place, who prevents dissolution. And Al-Qawi, the strong, the force behind all forces, the power that sustains every interaction in creation. The Quran says God holds the heavens and the earth lest they fall. Indeed, God holds the heavens and the earth lest they cease. And if they should cease, no one could hold them after him. Surah Fatir 35-41. Not metaphorically, structurally. The sustaining force that prevents cosmic collapse is attributed to divine will, to continuous divine action, to an ongoing creative act that holds reality together moment by moment. Stop the sustaining and the heavens fall. Remove the hand and creation dissolves. The force is not a mechanism, it is a will. It is an intention. It is a choice made every instant to continue holding. This is remarkably close to what entropic gravity implies. If gravity is emergent from information from the ongoing organization of bits on holographic surfaces, then gravity exists only as long as the information remains organized. Disorganize the information, and gravity ceases. The sustaining is continuous, active, present tense, not a mechanism set in motion at the Big Bang and left running. An ongoing process that must continue for gravity to exist, for the heavens and the earth to hold. In Judaism, the Talmud teaches that God renews creation every day, not that God created the world once and left it running. That creation is continuous, ongoing. Every moment, the world is sustained by divine will. If God withdrew attention for an instant, the world would cease to exist. This is not a passive universe set in motion by an initial push. This is an active universe sustained by continuous engagement. Gravity, the force that must operate continuously, that never pauses, that holds everything together at every instant, mirrors this theological claim precisely. Christianity teaches that in Him all things hold together, Colossians 1:17. Not that God created the universe and then stepped back. That the universe is held together continuously, actively, presently by divine action. The same force that created also sustains, also maintains, also prevents dissolution. The theological description of a universe continuously held in existence by a sustaining force maps directly onto the physical description of gravity as the force that continuously holds matter together. Buddhism teaches that all phenomena arise from dependent origination. Nothing exists independently. Everything arises in relation to everything else. And the relations that bind phenomena together, the connections that prevent the universe from being a collection of isolated, unrelated events, are not accidental. They are the structure of reality. The web of connection is the fundamental level. The individual objects are emergent. This is structurally identical to the view that gravity, the force of connection, the force of attraction, the force that binds, is emergent from deeper informational connections, from entanglement, from the quantum web that underlies spatial reality. Every tradition describes a force that holds the universe together, a sustaining principle, an organizing power, a continuous creative act that prevents dissolution and maintains structure. And every tradition attributes this force to something beyond the physical, to divine will, to cosmic order, to the fundamental nature of reality itself. Physics has discovered that the force that holds the universe together, gravity, might not be physical either, might not be a force at all, might be the emergent consequence of information organized in a specific pattern, information that exists on surfaces beyond direct observation, information whose organization determines the properties of everything we experience. The traditions said the sustaining force comes from beyond the physical. Physics is discovering that they might have been structurally correct. Now the honest assessment. The part this channel always insists on. The part that separates intellectual investigation from propaganda. We do not know if gravity is emergent from information. Verlinde's proposal is compelling but not confirmed. Jacobson's derivation is rigorous, but its interpretation is debated. The holographic principle is supported by ADS, CFT, but not proven for our universe. The connection between gravity and entanglement is established in theoretical frameworks, but not experimentally verified in the way that, say, gravitational waves are verified. We do not know if the fine-tuning of gravity implies design. The Entropic principle is a valid alternative. The multiverse might exist. The apparent tuning might result from mathematical necessity we have not yet discovered. There might be a deeper theory, a theory of quantum gravity that predicts the gravitational constant and the inverse square law, and the universality of gravitational coupling from first principles, in which case the tuning would not be tuning at all, but logical necessity, and the question of design would dissolve. We do not know if the parallels between physics and religious traditions are meaningful. Structural similarity is not identity. The fact that traditions describe a sustaining force and physics discovers a sustaining force does not prove they are describing the same thing. Humans find patterns. Humans project meaning. Humans are exceptionally skilled at seeing connections where none exist. Every coincidence is not evidence. Every parallel is not proof. But the direction of physics is remarkable. Classical physics removed God from the equations, made the universe a machine, made gravity a force, made matter fundamental, made consciousness irrelevant. 3 centuries of physics move steadily toward a universe that needs no designer, no sustainer, no purpose, no consciousness. Quantum physics reversed the direction, made matter informational, made space emergent, made consciousness relevant, made gravity the most fundamental seeming force potentially emergent from information, from bits, from data encoded on surfaces. And information raises the question that matter does not. Matter can exist without organization. A random pile of atoms is still matter. Rocks require no designer. Dust requires no purpose. Matter simply is. But information cannot exist without organization. Random bits are noise, not information. Information by definition has structure, pattern, organization, meaning. A random string of ones and zeros is not information. It is static. Information emerges only when the bits are arranged in a pattern that encodes something. That represents something. That means something. And gravity, if it is emergent from information, is emergent from organized information, not noise, not randomness, not static. Organized, structured, patterned data that encodes the specific properties of a specific force in a specific universe that produces specific outcomes. Who organized it? What organized it? How was it organized? Why was it organized in this specific pattern and not any of the 500 other possible patterns? These are not theological questions smuggled into physics. These are physics questions that happen to sound theological. And they sound theological because the physics has led us to a place where the structure of reality, the informational substrate from which gravity and space and time emerge, looks like the kind of thing that needs an explanation. That demands an explanation. That refuses to sit silently as brute fact. Organization raises the question of an organizer, not proves an organizer. Raises the question, opens the door, makes the question legitimate in a way that classical physics did not. Here is what gravity has taught us, stated as simply as possible. The most familiar thing in the universe is also the most mysterious. The force you feel every second of your life cannot be explained at the fundamental level. Newton could not explain it. Einstein improved the description, but could not complete it. A century of the most brilliant physics has failed to quantize it. Every attempt to reduce gravity to a particle or a string or a loop has either failed or remained untestable. And the most promising direction, the direction supported by Bekenstein, Hawking, Jacobson, Verlinde, Van Ramsdonk, Mulder-Sina, and others, is that gravity is not fundamental. That gravity is information. That the force holding you to the ground emerges from the organization of bits on a surface you cannot see. If this is true, then reality is not what it appears. The solid ground beneath your feet is not fundamental. The weight in your bones is not a force. The gravitational field that shapes the cosmos is not a field. These are emergent descriptions, like temperature, like pressure, like the smoothness of water, real in your experience, but not real at the deepest level. At the deepest level, there is information, organized information, structured data, a pattern from which space and time and gravity and the entire physical universe emerge. And the question of who or what organized that information is not a question physics can answer. Not yet. Perhaps not ever. The question lives at the boundary between science and something else, between equations and meaning, between data and purpose. Newton could not explain gravity, he said so honestly. Einstein improved the description but acknowledged it was incomplete. We have gone further than either of them. We have glimpsed the possibility that gravity is emergent, that information is fundamental, that the universe is built from data, not matter. But we have arrived at the same place Newton and Einstein arrived, at the boundary, at the edge of what physics can say, at the point where the equations go silent and the question begins. What is the information made of? Who wrote the pattern? Why this pattern and not another? Why a pattern that produces gravity, that produces stars, that produce atoms, that produce chemistry, that produces life, that produces consciousness, that asks these questions? Newton looked at gravity and saw God's hand. Einstein looked at gravity and saw geometry. We look at gravity and see information. Each generation goes deeper. Each generation gets closer to the foundation. And each generation, when it reaches the foundation, finds the same thing: a mystery, a question, a silence where the answer should be. 360 years since Newton watched the apple fall, 110 years since Einstein reimagined spacetime, 15 years since Valindi proposed entropic gravity, and the question remains, what is gravity made of? The answer, if we are honest, is we do not know. But we know more about what the answer looks like than any previous generation. We know it involves information. We know it involves holography. We know it involves entanglement. We know it involves thermodynamics. We know the answer connects the smallest scales, Planck length, quantum bits, microscopic degrees of freedom, to the largest scales, galaxies, cosmic web, the expansion of the universe. We know the answer will be strange. Stranger than Newton imagined. Stranger than Einstein imagined. Stranger, perhaps, than any physicist alive today imagines. Because gravity has been strange from the beginning. The most familiar force, the most constant companion. And at every level, Newtonian, Einsteinian, quantum, informational, stranger than the level before. And in that silence, every tradition, every prophet, every mystic, every sage heard something. Not equations, not data, not information, something else. Something that the organized information points toward but does not contain. Something that the emergent gravity reflects but does not reveal. Something that the entire structured, fine-tuned, information-based, holographic, entangled, observer-dependent universe seems designed to make you ask about. The force that holds you to the ground has been pulling you somewhere your entire life, not just toward the center of the Earth, not just toward the Sun, not just along the geodesics of curved space-time or down the entropy gradients of holographic surfaces. Toward this question, toward the edge of what can be known, toward the boundary between physics and meaning, toward the silence at the foundation of reality, where the equations stop and something else begins. Every step you have ever taken has been against gravity. Every breath you have ever drawn has been in the presence of gravity. Every thought you have ever had has occurred inside a brain held together by gravity. The force has shaped your body, your planet, your star, your galaxy, your universe. It has been the most constant presence in your existence, and after 360 years of asking what it is, the deepest answer physics can offer is organized information, which is either the most elegant reduction in the history of science, or the most profound pointer towards something beyond science that nature has ever provided. Maybe the question is the point.